Welcome back to the second video in our series on trigonometric identities. Last time we looked at what it meant to be an identity, when we might have had one, and also certainly when we didn't have one. And now we're going to change gears a little bit and start to look at what we can do when we have one, and also why we might want to have one. And more than that, how we might go about creating our own. So quite a bit to do about identities, perhaps to the surprise of no one, but here we go. So first off, a little motivation, a little reason why we might want to have identities on our hands. Suppose for instance, I had this expression at hand, tangent of theta plus cosine theta over 1 plus sine of theta. So that's an expression, obviously, and if you want to pretend it's part of a function, go for it if that makes you feel better, but it's just an expression I kind of made up. And at the same time, maybe I didn't. We'll see about that later. But suppose I wanted to evaluate that expression when theta equals pi over 3, which is just some value I can put in for theta. Obviously there was others, but let's say I just wanted to do this one for now. Well, remember that tangent of pi over 3 is, let's see, root 3 over 2 over 1/2, it's the square root of 3. The cosine of pi over 3 is 1/2, and the sine of pi over 3 is the square root of 3 over 2. So all of that boils down after substitution, root 3 plus 1/2 over 1 plus root 3 over 2. And I'm sure that simplifies to something. And I don't want to do that right now, so I'm going to make you do it. Take a minute and give me the number that's going to come out, the one single number that comes out in simplest terms after you evaluate pi over 3 for theta. Tell me what you get, and then I'll tell you what I get. So here we are. I'm now evaluating the trig function for when pi over 3 is theta. The trig function in question being tangent, cosine, and sine, and then finally putting all that together for our expression in question. Don't mind this calculator of uncertainty. We'll see as it gets revealed what I've got. So first of all, like I said, just do the evaluations. Root 3 for tangent, 1/2 for cosine, root 3 over 2 for sine. And then, recognizing this is a compound fraction here, I can clean that up a little by taking the half, or the 2 in the denominator of the numerator, which is a mouthful, I admit, and moving that down into the denominator, giving me root 3 plus 1 over 2 plus the square root of 3. Okay, we're getting there. And now you could recognize, okay, I have a sum of 2 fractions here. And to add those together, yes, I would need a common denominator. But before we do that, and just wanting to do one for old time's sake, suppose I wanted instead to first rationalize the denominator of this second fraction here. So to do that, I would need to multiply by the conjugate, 2 minus root 3, and that would have to happen to the bottom and the top of that fraction, giving me, for the numerator, 1 times 2 minus root 3, or just 2 minus root 3. And the denominator being a difference of perfect squares, it's going to be 2 squared minus root 3 squared, 4 minus 3. So all this now is root 3 plus 2 minus root 3 all over 1, or root 3 plus 2 minus root 3, and those do cancel, leaving us with exactly 2. Well, that's neat. And at the same time, maybe it's a little sad because that nice number came about through 7 steps, maybe more, depending on how you qualify a step. That's way too long. I mean, think about it this way. What if I had to evaluate the same expression for a dozen values for theta, or 100 values of theta? I would have to do those same 7 steps hundreds of times. There's got to be a better way. And indeed there is. I know you're excited, I'm excited, so let's have a look at it. So we've got some ideas now. The idea being, maybe it's going to be possible for us to do all of those steps that we did previously, all that arithmetic. Maybe we can do that symbolically. Maybe we can do that without having to crunch a single number, and then having done it once, we'll never have to do it again. That's the end goal here. And hear me out, let's see if it can happen. The idea being, I want to simplify my expression as much as I can and get it reduced down to something as simple as possible. And there's a few general strategies for this. There are going to be strategies that we'll see again in the next bit where we're starting to prove existing identities. But when we're going about making our own, it's also going to be a good idea to, at times, take all of the trig functions and just rewrite them to sines and cosines. Just break it down into the simplest bits. Also, we might avail ourselves of combining more than one fraction, if we have more than one, into just one single fraction. And of course, we can also work smart and not hard and use existing identities, such as the Pythagorean identities, to kind of clean things up nicely as well. And then lastly, once we do have everything factored and written up, we can in fact start canceling things off and getting to simpler expressions. So let's see what I mean. First things first, when you're not sure what else to do, just always write everything in sines and cosines. So tangent of theta does break down to be sine over cosine. And I have the same second term as before. But now I recognize I have two fractions, and they need to be combined into one. Or maybe at least they should be. We'll see what happens. So to combine these two fractions, I would need a common denominator, and the least common denominator between cosine theta and 1 plus sine of theta is just their product, cosine times 1 plus sine. So to turn this first fraction into having that denominator, I would need to multiply top and bottom by 1 plus sine of theta. And to get the second fraction to have that same denominator, I would need to multiply top and bottom by cosine of theta. And we do a little bit of algebra. Distribute the sine theta across, and we'll have sine theta plus sine squared theta. And then, of course, cosine times cosine gives me cosine squared. But now I've got two fractions that can be added together, so let's go for it. That's all one numerator over one denominator. Sine plus sine squared plus cosine squared, all over the same denominator as before. But here's where things get interesting. I can use existing identities. Specifically, the Pythagorean identity, sine squared plus cosine squared is equal to 1. So by that substitution, I get sine theta plus 1 over 1 plus sine theta times cosine. Well, sine plus 1 is the same as 1 plus sine. So I can actually cancel those two factors off, leaving me just with 1 over cosine theta, quite simply known as secant of theta. And so if you wanted to evaluate this original expression at pi over 3, you could have just simply evaluated this expression at pi over 3. They give you the same value. In fact, you could do anything for secant of theta and get the same value out as you would have for tangent of theta plus cosine over 1 plus sine. And you would get there much, much faster. So hopefully we see the value of having identities to kind of save on computation time. Hopefully. Let's find out. And one last thing before we're done with this bit of a cautionary tale. I know that this is not the algebra side of pre-calculus. That's pre-cal 1 or math 1710. But that said, the algebra techniques that you learned in that class carry over here. And more importantly, you got to be right. You got to make sure the algebra you use, the techniques you employ, are actually sound mathematical techniques. So a few cautionary tales, a few words of warning here. First of all, consider this slightly different expression from before. Tan theta equaling sine cosine over 1 plus cosine. Same bit as before, rewrite it like this, with sines and cosines instead of anything else. But the first bit of warning, cancel factors, not terms. And this is something I have to scream at with my algebra students, so I'll scream at it with you here. This left fraction does not reduce down to be sine theta over 1. These cosines do not cancel. And that is because they're not factors. Order of operations tells me I have to add 1 to cosine. And that happens after I do multiplication. So I'm not at liberty to cancel off via multiplication something that's not being multiplied. So this is not true. But even if it were true, this in turn would not turn into sine squared over cosine theta. You gotta know the difference between multiplying fractions and adding fractions. This is what you would have gotten had you multiplied sine over cosine times sine over 1. If you wanted to add these things together, you would have to have a common denominator first. And lastly, just to have said it, don't do whatever this nonsense is. I have had students, and I don't want you to be that student, who forgets that sine and cosine are things, and rather thinks they're just a triple of letters, s times I times n squared of theta, divided by c times o times s of theta. I have had students, and I don't like seeing it for obvious reasons, that they would try and cancel the thetas and try and cancel the s's of sine and cosine, leaving with n over co. That is utter nonsense, and it makes me sad. It does. And to close us out here, we have now established that you can make your own identities by doing appropriate algebra techniques, and what we're going to see going forward is that we can take existing equations and prove that they are identities by using those self-same techniques. And just a reminder as always, saying that I was not able to prove something is not compelling enough reason to say it's not true. Or rather, also that it is true, right? Not being able to do something does not prove anything other than the fact that you weren't able to do it. So in the next section, we are going to try and maximize our chances of doing as much as possible. So look forward to that. See you then.